Hi, my name is Lior Solotkin. I'm a master's student in Tel Aviv University. I'm going to present my supervisor, Professor Rotem Oshman, and my work. The work combines game theoretic settings into distributed computing. There is a decent amount of works in game theory in distributed computing. This works solves different kinds of problems like leader election and information dissemination, and in various network topologies. The main caveat of most of these works, the solutions are uniformly random. So they ignore the utilities of the players, which is an essential topic in game theory. Our work solves the information dissemination problem. This problem is a central building block in a lot of distributed algorithms and a goal itself. We want to model it in game theory settings. So we will model it like a Bayesian game, and we will implement an information mediator for this game. This we will define later on. Prior work that dealt with the information dissemination problem in game theoretic settings is Afek et al. They solved it for a various network settings, but their assumption that the player has no incentive to lie about his input unless he got all other players' input. We solved this problem in asynchronous general graphs. Our assumption is that a priori, the agents have no incentive to lie about their types, but once he learned any kind of information about others' input, he may have incentive to lie about his input. Now, let's define a Bayesian game. We will define it not formally, but by an example. So, as any game, Bayesian game consists of a set of players. In this example, 5 players. Each player gets an input, a type, by the nature, which drawn from a set of possible types for each player. It's drawn by probability P. Then each player needs to take an action from a set of possible actions. And in the end, each player gets a payoff according to a utility function. This is a function of all the types and all the actions that was taken. A player, a rational player, wants to maximize this function, the payoffs that it's going to get. Now we know what a Bayesian game is. We can formulate now the information dissemination problem as a Bayesian game. So this time, the input of the players are the types. And the action of each player is to output all the types, the inputs of all players. We added a punishment action, the abort action, and it can be used as a threat. The utility function depends on all the types of all players and the output of the player. Our assumption is that the punishment action exists and it will give the minimal payoff to all the players if one player takes it. All the players have incentive to say their truthful type a priori. And when they learned all the information, they have incentive to tell the true information they learned. Another game theory concept that can be useful in our work is a mediator. A mediator is a trusted entity that all players trust. So it starts like a regular Bayesian game. Each player gets a type. But here there is another phase where each player sends a type to the mediator. It should be the truthful type, but a rational player can lie about it. Then the mediator computes a function D, which inputs the types and outputs actions. Then the mediator recommends each player with a type privately, with the action privately. Then each player take an action, not necessarily the recommended one, and get the payoffs according to the utility function. We defined a general mediator, but most of the mediators are not interesting to be simulated, just the good ones. A good mediator follows the communication equilibrium. Communication equilibrium is when the incentive of the players is to tell the true type to the mediator and then follows the recommendation action. So this mediator is called a communication equilibrium. Several works in the past implemented a mediator in a network, but they consider a fully connected network. We allow general graphs. They consider a coalition deviations and unexpected players. We didn't consider these settings. They used MPC, which requires a high bit and round complexity, which we tried to decrease. And their solution protects the types of the players. That is, no players, no others types, even in the end of the game. Our protocol does not save the types. In the end of the game, the player knows all others players' type. Our goal is to implement a mediator for the information dissemination game. So we can define a specific mediator for this aim. We call it an information mediator. It starts as a regular mediator. It gets types from all the players, but this time he does not compute anything, but he sends the types of all the players to each of the player. And the action of the players is as in a game of information dissemination, just to tell the types of all the players. In the information dissemination game, as we defined it, no player has incentive to lie about his type before he gets to know any other information. So we know that the players will send the real type to the information mediator, and the utility function gives the players incentive to tell the true type that they learned. So we know that the action will be outputting the true types. Once we implement the information mediator, we can use it to simulate much larger class of mediators. How can we do it? So originally, the mediator got the types, and by the types computes the function D. So with the information mediator, all the players get to know all the types, and they can compute the function D by themselves. And then they can go and act according to the recommended action. Can we simulate any good mediator? Any mediator that follows the communication equilibrium? So this is not the case, since before the player just got to know the recommended action. This time the players got to know all the types and they compute all the recommended actions. So they get a much larger information. So we need to tighten our definition of mediators that we can simulate. We call this class a full information communication equilibrium. The first condition is the same. The incentive of the players is to tell the true type if they don't know anything else. But this time, even if they got to know all the types and all the recommended actions, they would follow the recommended action by themselves. Now we know that the full information communication equilibrium mediators can be simulated by the information mediator. So we can ask what kind of problems can be converted to be used with the full information communication equilibrium mediator. We found two classes of problems like this. First is the constrained games. In these games, a specific player doesn't have an incentive to deviate from the recommended action if all the other players follow the recommended action. For example, the agreement problems, right? The leader election or consensus. If other players chose specific leader, the one player does not have incentive to deviate from this leader. Any other problem can be converted into the constrained game if the output of one player should contain the output of all of its neighbors' output. Another class of games that this mediator can be useful is the class of games where the utility function is local. I mean, where the player is influenced just by his type and his action. Other players' outputs and types don't influence his payoffs. For example, the resource allocation problems. Okay, so now to the protocol itself, and first the model assumptions. We assume that the network graph is known and all the subgraphs that we will need during the protocol is pre-computed. The graph is two vertex connected, that is, the graph remains connected even after removing a node from it. The network is asynchronous, and there is a punishment action, that is, each player can take an action that will give all the players the minimal payoffs. The protocol, the goal of the protocol is to simulate an information mediator. And the main two ideas of the protocol is first that each player commits to his type before he gets to know any other player's information. And that after he commits to his type, he has no incentive to lie about it. The protocol consists of 5 steps. The first step is committing on a cycle. The cycle is pre-computed, and only players 0 and 1 are going to be committed in this step. So let's see on a cycle. First, player 0 XOR his type with a random key, and player 1 XOR his type and a bit string v that we will need in further steps with a random key. Player 0 sends his encrypted data to player 1. Player 1 receives it and sends his key to player 0 and his data to player 2. In this moment, player 1 is committed to his data because all his data to recover his type is already out. Player 0 gets the key and sends his key to player 4. Player 4 waits to receive the encrypted data of player 1 and sends the key and the data to the other players. So here, player 1 receives the key, and now player 1 can compute the type of player 0. Player 0 receives the encrypted data and can compute the type of player 1 and the bit string. Now, the second step. The second step is going to be a commitment on a tree. The tree consists of all the players, excluding player 1. The tree is pre-computed, and player 0 is the root of this tree. The algorithm is executed by a parent and each of his children. Then the child becomes a parent and he executes with each of his children. The main idea is that only when a child commits to his type, he can become a parent. We will see how it works. How it works, the parent encrypts his type by V, and sends the encrypted type to the child. The child receives it and sends his type to the parent. The parent receives and sends his type to the child. Now the child can compute V. After he computes V, only now he can execute the parent's algorithm. The V will be checked in the end that the child uses the right V. The next step is going to be revealing the types. It's just broadcasting the type up the tree and down the tree, this time including player one. In the end of this step, all the players know all the types, including V. Step 4 is consistency check. In this step, each player will send all the data of the types and V to all of his neighbors, and we receive the data from them, and we'll check that the data is consistent. The main idea is that between two neighbors of I, there is a path excluding I. So I cannot send different data to J and K, since in this path that without I, it will be revealed. The fifth step is to take an action. First, if a deviation was detected, just take the punishment action. And here we can end with the information game, since each player has all the types of all the players. But if we want to play more general game, that the mediator there is a full information communication equilibrium, each player can compute his recommended action by the mediator, since he has all the types, and just act according to this mediator. Since it's equilibria, each player will follow this recommendation, even if it's know all the types. This ends all the protocol. We can improve this protocol. The message complexity is big O n, but in step 4, the message complexity is big O n squared, since each player sends to all of his neighbors the message. But any two connected graph has a subgraph, which is also two connected, but with only n edge, big O n edges. We can use this subgraph, and then the message complexity becomes n messages, which is optimal. Now I want to show you why the assumption of two connectivity is necessary. For this, let's look at a two players game. Each player will get a type or 0 or 1 with uniform probability, and an action or 0 or 1. The utility functions are defined by those matrices. When the types are 0, 0, this is the relevant matrix. And if both players take the 0 actions, these are the pairs, 1 and 1. The Nash equilibrium for this game is to play the other's player type. Let's look at a specific example where both types are 0. At the beginning, each player thinks that the other type is 0 with probability half. Let's look what player 0 thinks. He knows his type, so these are his matrices, but he doesn't know the other's type. What does he know? That he wants to take the other's type action, and he wants to influence others' action. If others' type is 0, he wants that the other's action will be 1. So he wants to influence and to lie about his type. But if others' type is 1, he wants to tell the true type. We are joining the game in the middle, but still each player does not sure about others' type. Now player 1 sends a message to player 0, which reveals that the type of player 1 is 0. Now player 0 knows that he needs to look at this matrix, and he knows that he wants player 1 to take the action 1. So he will send messages which will influence player 1 to think that his type is 1. He can't do it because player 1 still does not know what is the actual type of player 1. Now he convinced player 1 that his type is not 0, so his type is 1, and they take the action 0 and 1. If they took the action 0 and 1, the payoffs are 2 and -2. So instead of getting 1 and 1, player 0 got 2, but player 1 got -1, -2. For conclusion, we gave a truthful protocol for information dissemination, and we did it in game theoretic settings, in asynchronous and general networks. We assumed that the graph is too connective, and it's a necessary condition. We showed it. We got an optimal bit and round complexity. We introduced a new solution concept, the full information communication equilibrium, and we showed that it is useful in many problems in distributed computing. Future work that can be done in this area is to extend this work to coalitions and Byzantine players, and maybe to find new problems that can be compatible with the idea of full information communication equilibrium. That's it. Thank you very much.